Let's examine the engineering and physics behind speed. In automotive design, speed isn't just about raw power, it's a complex interplay of mechanical, electrical, digital systems, and the fundamental forces of physics working in harmony. For engineers, true speed is measured by how efficiently a vehicle converts stored energy into forward motion, while overcoming forces like friction, drag, inertia, and gravity. Traditionally, fast cars relied on large displacement engines, think roaring V8s, where combustion fuel delivery and mechanical gearing determined acceleration. The visceral experience of noise and vibration was a byproduct of these mechanical systems pushing their limits, all while battling friction in the drivetrain and the inertia of the car's mass. From an engineering and physics perspective, acceleration is about torque delivery, traction, and overcoming inertia, the resistance of the car's mass to changes in motion. The faster a car can transfer torque to the wheels without losing grip, the quicker it accelerates. Friction between the tires and the road is essential for traction, but too much power can cause wheel spin, wasting energy. Enter electric vehicles. Unlike combustion engines, electric motors deliver peak torque instantly, with no need for multi-speed transmissions or complex gear changes. This means EVs can overcome inertia more rapidly, launching off the line with impressive force. However, they still must contend with friction, air resistance, drag, and gravity, especially when accelerating uphill. The absence of engine noise in EVs highlights the efficiency of their powertrains. Electric motors convert over 85% of electrical energy into motion, compared to about 30% for internal combustion engines. This efficiency means more energy is available to overcome drag and friction and to accelerate the car's mass. Modern performance is now defined by kilowatts, battery chemistry, and power electronics. Engineers focus on optimizing battery output, motor control algorithms, and thermal management to push the limits of acceleration and efficiency, all while minimizing losses to friction and heat. Software integration is a game changer. Advanced control systems manage everything from torque vectoring to traction control, ensuring that every bit of available power is used efficiently and safely. These systems also help manage the forces of friction and grip, maximizing acceleration without losing control. When you press the accelerator in an EV, sophisticated software instantly calculates the optimal power delivery, adjusting for traction, battery temperature, road conditions, and even the effects of gravity on inclines. The result is seamless, relentless acceleration with physics and engineering working together. Let's look under the hood and explore how electric motors, advanced batteries, and integrated software are redefining automotive performance. The future of speed is not just electric, it's engineered, optimized, and digitally controlled, with every force of physics taken into account. Let's break down the technical differences. Under the hood of a petrol car, you'll find a highly intricate mechanical system. Internal combustion engines rely on a sequence of fuel injection, spark ignition, and controlled explosions to drive pistons, which then turn a crankshaft. This process involves numerous moving parts, valves, camshafts, gears, all synchronized mechanically, with each step introducing friction, heat loss, and mechanical inefficiency. Every stage in a combustion engine, fuel metering, ignition timing, and gear changes, requires precise mechanical coordination, often managed by analog or basic digital controls. This complexity not only increases energy loss, but also limits how quickly power can be delivered to the wheels. And in contrast, electric motors are fundamentally simpler. Electricity flows into the motor, generating a magnetic field that spins the rotor directly. There are no explosions, no multi-stage gearboxes, just a direct transfer of energy to motion with minimal mechanical loss. The real advantage comes from software integration. Modern electric vehicles use advanced control algorithms and real-time monitoring to optimize motor efficiency, torque delivery, and energy usage. With fewer moving parts, the software can precisely manage power output, regenerative braking, and even traction control, all in milliseconds. In petrol engines, drivers must build up engine revolutions to reach peak torque, and the response is limited by mechanical lag and gear ratios. Even with electronic controls, the process is inherently slower and less adaptable. Electric motors, managed by sophisticated software, deliver maximum torque instantly from 0 RPM. The system responds to pedal input with immediate precision, adjusting power delivery in real time for optimal acceleration and efficiency. Think of it as the difference between waiting for a chemical reaction and executing a digital command. Software-controlled electric motors react instantly, while combustion engines are bound by physical processes. In a real-world comparison, an electric car's software-coordinated powertrain launches the vehicle forward with no delay, while a petrol car's acceleration is limited by mechanical and thermal constraints. This seamless integration of hardware and software is why electric vehicles achieve such rapid, efficient acceleration, delivering power instantly and intelligently every time you press the accelerator. The real advantage? Instantaneous electric torque, precisely managed by advanced software. Torque is the rotational force that propels the car forward. Imagine the twist needed to open a stubborn jar, but delivered to the wheels. In petrol engines, torque builds gradually and peaks mid-rev, requiring careful throttle and gear management. Drivers must shift gears to keep the engine in its optimal torque range. Electric motors, however, can deliver peak torque from 0 RPM, thanks to their design and real-time software control. When you press the accelerator, sophisticated algorithms instantly modulate power delivery, maximizing grip and minimizing wheel spin. This precise control is why EVs launch so explosively. Software ensures every bit of torque is used efficiently from the very start. The result? Seamless, rapid acceleration, no gear changes, just continuous software-optimized speed. When analyzing the Tesla Model S Plaid alongside traditional high-performance petrol-powered sports cars, the differences extend well beyond their powertrains. This comparison highlights not only divergent engineering philosophies, electric versus petrol, but also the critical role of software integration in modern vehicle performance. The Tesla employs a tri-motor all-wheel drive system, managed by sophisticated software that precisely controls torque distribution and power delivery. This system, powered by a high-capacity battery pack, produces up to 1,020 horsepower with instant torque. In contrast, traditional petrol-powered sports cars utilize high-output engines, with torque building as engine speed increases and mechanical systems respond. A key technical distinction is the torque curve. Electric motors, governed by real-time software algorithms, deliver maximum torque from 0 RPM, enabling immediate response. Petrol engines require revs to build before reaching peak torque and rely on mechanical systems for power management, resulting in a delay. In terms of acceleration metrics, the Tesla Model S Plaid achieves 0 to 60 miles per hour in under 2 seconds, a result of both instant torque and advanced software optimizing traction and power output. High-performance petrol sports cars, while highly capable, are limited by the mechanical lag inherent in petrol engines and traditional traction management systems. Drivetrain efficiency is further enhanced in electric vehicles through software-controlled single-speed transmissions, which minimize energy loss and streamline power delivery. Petrol vehicles require complex multi-speed gearboxes to maintain optimal engine performance, introducing additional mechanical losses and less precise control. Electric drivetrains, managed by integrated software, convert over 85% of stored energy into motion, while petrol engines typically operate at 25 to 30% efficiency due to heat and friction losses that software cannot fully mitigate. Regenerative braking, coordinated by vehicle software, allows electric cars like the Tesla to recapture energy during deceleration, further improving efficiency. Petrol-powered cars rely solely on friction brakes, which dissipate energy as heat and cannot be recovered. Ultimately, the integration of advanced software in electric vehicles is redefining performance metrics. Instant torque, higher drivetrain efficiency, and intelligent energy management systems provide electric cars with a significant technical advantage in responsiveness and overall driving dynamics. As automotive technology evolves, the synergy between hardware and software in electric vehicles is setting new standards for efficiency, control, and performance, quietly, intelligently, and with unprecedented speed.